Um, what's up, guys? So wait. Okay, so we're back doing some more coding. Um, so I've done 4 problems today, and um, wait, maybe I'll show you this. So I've been doing some thinking, and I wanted to do a new format on how I want to approach the studying stuff. So I've compiled a list of interview questions where there's a lot of different topics, and I've done the Neat Code 250. So I know all the different concepts or different data structures that you can use. Maybe not at the deepest level, but at a level where I think I can attempt some problems because I've solved a bunch of problems already. So I have that. Then I have my DP greedy, and I've added graph problems, and I'll do one of oh no, I'll do one of each of those topics every day, hopefully, and I'll do one of the interview ones. So yeah, so I've done 4 today, but I feel like it's either I'm working really inefficiently, but I feel like I've done basically nothing today. Um, okay, yeah. Well, we'll start with this one. So again, I'll just assume that you've read the problem. So initially, I was thinking um, that to make a tree, if you have n nodes, um, if you have n nodes, so let's say n equals 4, to make a tree, you would need n minus 1 nodes. I mean n minus 1 edges to connect all of them. Um, but obviously, and then I had this case where if our m equals n minus 1, so equals 3, we can just um, what is it, exit out early. And I thought that was right, but I don't think it is quite right because yeah, because let's say for example we have 5 and 6. What is this? 5 and 6. So yeah, clearly this isn't fully connected because if we start at 4, we can't end at 2. There's no road leading them together, right? So yeah, and this is we have 1, 2, 3, 4, 5 edges here. So obviously that hypothesis was wrong. So instead of that, I thought about using the union find data structure because it can basically group these nodes into components. So here we have one component here, one component here, and as long as there's a road which can or an edge connecting any one component to the other, if we're at 4, we can go to any node that we want. Um, yeah, we can go to any node that we want. So my game plan here was to basically um, have our union find data structure initialized, and then every m for every m edges that are already present, we just union find that, and then we'll find a list of components, or like a components, and then we'll find a list of their parents, like the head of that component, or like the root of that component, and then based on how many different components there are, we have to connect them. So it'll be the amount of components we have minus 1. So I'll show you the code for that I wrote. Yeah, so I'll just bring it here. Yeah, so you have your union find data structure, right? And then you have your n and your m, and then you initialize it with n. And then for every edge, every edge we connect it, And this is zero index, so I'll just make this zero index because they give it to you one index, right? And then the unique roots is just basically this find will find the parent of like this node, and then we put that in a unique set, and then this is our k. And yeah, as I said, and then that's how many edges we need. And then if that's not zero, then we honestly don't even need to union them. We just need to print them, because yeah. And then that's how you do it, because you have these different components, and you actually only need one edge between all of them. So yeah, I mean, this one was pretty simple, I would say, a lot simpler than everything else that I've done. I kind of want to see how hard it was. Oh, there's no difficulty. Yeah, but I don't expect it to be too hard. That seemed pretty fine to me. So yeah, next problem. Let's see. Oh yeah, this one. Um, this one is a classic greedy. Well, maybe not classic greedy, but from how I saw it was, um, yeah. So you have like you can categorize the characters into two categories. So you can have like unique characters. Whoa. Yeah. So you can have unique characters, and then you can have non-unique. Um, for these non-unique, they'll be greater or equal than 2, right? And we can only take a maximum of 2 from these non-uniques, because that's just based on the problem, because two letters that are painted the same color, or for every letter that is painted the same color, they have to be different letters. That means, let's say, um, we have this string that they gave us. How do you change color? Green. Okay. Jet. And then K A, right? So this would be invalid because these two are the same characters, but they're also the same color, right? And we want to make it so the amount of greens and reds are the same, right? So how I thought of that was for all these characters that are greater than well, okay, wait. Firstly, we want to basically determine the amount of red characters, and we don't necessarily really have to calculate the green ones because you'll see why later. Okay, so these non-unique ones. So because we can only have one letter, which is one color, we can take a max of 2. So like from these, so 1 will be green, and then the other character will be red, and then everything else will be uncovered. I'll just do no. Yeah, everything else will be no color. So how would this look as an example? So see how we have 3 A's here? We can pick 2 of them to have colored, like A green, and this one can be green, and they can be adjacent, it doesn't really matter. But yeah, we can pick a max of 2, because if we pick any more, then we won't have 2 colors. So exactly, yeah. So this white would have to either be green, which would mean that there's 2 letters that are painted the same color, which is we can't have that, right? So that's that. And then the unique colors, the way we can keep them the same, like we'll either have an even amount of unique characters. So let's say we had 4 unique characters, right? This means that two will have to be red, and then the other 2 will have to be green, because we want the coloring to be equal, right? So yeah, and then in the case that let's say it's odd, it's 5, we can only take 2 of each. So we can only take 2 of each. So what I'm trying to say is, we'll basically count all the colors, and once we've done that, the non-unique ones we can only we'll, we'll add the amount of non-uniques we have. We'll add that to reds, right? Like the different characters. So we'll give them to red, and we'll also give them to green, right? And then for the unique ones, we'll split it in half, but we're gonna use full division because of this case. For when it's odd, right? We'll get full division, so we'll have half of them go to red and half of them go to green. So yeah, that's basically how you do it. Let's see if I found. I'm pretty sure I did write the solution for this as well. Yeah, so you have, is it n test cases? Oh, n words, right? Yeah, n words. So you have this counter, and then this res is like the what you return, right? So this counter just counts all like the current. It creates a dictionary with the frequency of each character, right? So if that character is greater or equal than 2, that means each color gets 1. So this res gets 1, and then otherwise it must be that it's unique. So we'll add 1 to the unique ones, and then we'll add the amount of pairs, like the amount of pairs like of 2, plus the unique full division by 2. And yeah, that one was pretty simple as well. Classic. No, I don't know about classic greedy, but like it makes sense on why you can be greedy there, because it doesn't really matter like if you pick like I don't know, like green, red, white, something like that. So yeah, so that's pretty simple. This one was the interview one. I remember this one. So I'll show you my submissions. This was my first one. It was very brute forcey, so it did pass, but it wasn't very good. And I was kind of stuck on how to find like a better solution, so I looked it up, and I'll explain that solution now. So what I've done is I've just in a window of like from like for every, well, okay, well, I'll use an example. So like is squirrel. Yeah. So yeah, for every subsequence of size a, like length of a, right? We just checked if it equals a, and if it does, then we'll save that index into like an index. Actually, it makes more sense to do the b word. Yeah. So of size of word of size length b, right? We just see if it equals b, and then if it does, we save it there. And then for every and then we'll look at every subsequence of size length a, right? And we'll check if it equals a. And in the case that it equals a, what I did initially is I just checked every index b. If that index b is within k of our index I, that means we found one, and that index is good, so we add it to our result. And yeah, and then basically what what the other algorithm did was essentially just make the searching process a bit faster. So yeah, so where's my, here, okay. Yeah. Okay. Yeah, this is gonna feel like it's gonna take a while. It's 4 and 18. Okay, I'm just gonna use this as an example, right? Okay, so let's say we stumble upon um, a subsequence of size length A at index 16, as it says in the first example, right? 16. So ideally, we want to find an index for J, right? So we want to find an index J such that it's within 15 of 16. So we're basically looking for an index between 1 inclusive and what is that, 31? Yeah, and 31. Right? So we'll search for 1 first, right? And we'll basically use binary search to find a position where this 1 could like if we were to insert it into the list, where does this 1 belong in, right? And we'll find that it equals 0, right? And in that case, that means that um, this 4, right, what's currently at 0, is greater than 1. And what that means is that we found a number which is greater than our lower bound of 1, and now, which yeah, it is greater than our lower bound of 1. Then now we have to check if it's lower than our upper bound, right? Because let's say this was this case of 50, 51, right? We would get this. We would still get 0, but so yeah, firstly, this 50 is greater than our lower bound, but we have to check if it's greater or if it's less than our upper bound of 31, right? Yeah, and that's it. And if it were that we get an index which is equal to the length of our list, that means that it's bigger than every like it's wait. Yeah, okay, yeah. If it ends like at the length of our index j's, which means it's out of bounds of that array, it just means that wait, everything is too small. Like everything is smaller than our um, index I minus k. So we do nothing. So that's essentially what I've done. I'll show you the code. So firstly, we're just building the this is just building the index j array, and then for every I in this range, and I've gotten this range because of this, where it says I is beautiful if it's less than or equal to length s minus length of a. Yeah, so we're checking if it equals a, and this bisect left just finds the index where it should be like inserted if it were to be inserted, I think. And yeah, and then we're just checking if it's less than if it's in bounds, and if the whoa, what's happening? This k value is bigger. This I plus k value, like our upper bound, is less than the number that it's currently at, and that accepts, and it does pretty well. And it makes sense. That's definitely a technique that I haven't seen yet, but it does make sense. I can see why. Yeah. Cool. Next one. So this is actually, I coincidentally got this question, but we did this yesterday as well. And I have read the solution. I didn't even attempt the problem because I was meant to read the solution last night, but I actually didn't. So that's okay. And I haven't coded up. Mm, I might just save this. I won't code it up because honestly, if I remember it. But the solution is along the lines of we have our tail. We have this array called tails, and what this represents is like at this at index one. I'll just say it's one index, right? At index one, we want to see um, what's the smallest number we can have at our first index of our subsequence, and then it goes the same for 2 and then 3 and 4 because we want a lower number because it has a higher chance to um higher chance for it to be a like higher chance for it to like have numbers that are bigger than it coming, right? um Yeah, because let's say like in our first position we can have a 3 or a 5. I was gonna pick the 3 because the 3 means that let's say we encounter a 4 in the future. It's more likely that um, well, it's not more likely. It just means like it's easier to find a number that's bigger than 3 than it is for 5 because 5 is bigger than 3. And yeah, so every time we have a number, we check that well, firstly we check if it like if we found numbers that are like smaller than it, right? So I'll just use an example. I'll just use an example, okay? So we have 3 um oh, it's raining 3 yeah, so wait, so 3 3 4 7 5 6 8, right? And um we want to yeah, so this first number, it has nothing to compare it to, so we'll just add it. And then 3 is the same size as 3, so um we don't have to change anything. I mean, we could, but it doesn't matter if we change it. And then this 4, right? This is bigger than 3, and basically we'll do the same thing. Since like this is sorted, we'll use binary search again to find like the potential position of this 4, right? In this case, we'll find that it is equal to 1 because it's bigger than everything in the current tails list. So we'll add 4 to the end. But in the case of, let's say this is a 2 instead of a 4, right? We'll find that the place we need to insert it is at 0. And that basically means that this number is less than the number that we're currently at. So because 2 has a higher potential for it to be increasing, we just change this 3 to a 2, right? But yeah, so every time we find a number that is less than the number at a current position, we replace it. Otherwise, we extend our tails array, right? So 5. 5 would be 5 would be here because yeah, it's smaller than this. So in this case, we would replace 7 with 5 because 5 has higher potential for a number to be upcoming and be greater than it, right? Wait, why does it say? Why is it? It's only 4. 2, 3. Yeah, is this the right question? Or is this the same question as the weak code one? I just kind of assumed that it was. But either way, I'll just say I'll explain the weak code one because I think they're very similar. I haven't even read this. I kind of saw that they were similar and I just kept going. I just didn't bother because I didn't even read the solution for last night. Yeah, but anyways, back to what I was saying. It's so like the maximum subsequence would be the length of this tail, and the strategy that we want to use is that every time we find a bigger number, we will add it to the end, but every time we find a number which is less than what's currently in the tails array, we replace it. Uh, because that number has higher potential to be like um, higher potential to be like a new number, like for like another number to be um, greater than it, right? So kind of what I was confused by initially. Because, wait, isn't this? Yeah, I'm not gonna read this problem because I think it might be a little bit different. But from the lead code one, let's say we have 6, 8, right? But then we have 1, 2, like after the 8, we have 1, 2, 3, 4, 5, and 6. So what we do in this case, I'll just rub this out, is we just replace the numbers anyways. So 1, 2, 3, 4, and I'll stop at 5, right? And the reason why we're able to do this is because um, uh, is because yeah, so like at length 1, like we're not really like um we're not like how do I say this? Actually, I don't think it'll work for this problem, but the reason why we're able to do this is because this doesn't really change like the length of um the length of the subsequence in a way. It just allows for potentially an upcoming subsequence to be greater than it, right? So like if we like if this 6 was instead um 9, uh you could actually add it to both subsequences. But actually I don't fully know, to be honest. I don't know. Like no, I can see why you can replace it because like um these subsequent, like obviously if 9 is, well, mm, because it's like the number at the last index is really important because um we don't want to stick with this solution and like not change it because it has less chance for a new number to be greater than it. So we'll just change it, right? But let's say yeah, and we know this 5 will never be inserted here because of the way we find the index where we replace it. We find like the least, the smallest index such that the number at that index is greater or equal to it, to the number, right? So if we're looking at this and we insert a 5, well, let's say, yeah, we insert a 5, the 5 would be here. It wouldn't go here because of the way we're finding where the 5 should be, right? So it's fine to do that because yeah, what I mean, like the reason why we inserted 5 here was because we found 4 numbers before we found this 5, such that there's a subsequence. of it, if that makes sense. So yeah, the only thing I'm a bit confused about in this question is why is this not 5 numbers? Because I can see you can put 3, 4, 5, 6, 3, 4, 5, 6, 8. So you can erase any element, but not necessarily going successively. Yeah, so it's the same thing. So why can't you do yeah, I'm not too sure. Two, three, I'm not sure. Not sure why the first case isn't. I don't get why the first case isn't 5. I mean, am I crazy to say that 8 is greater than 6? You need to choose some sub. Oh, okay, yeah. This is very different because you have to have. It has to be consecutive integers, so it's like 1, 2, 3, 4, 5, or like 1, 2. Yeah. Okay, that makes sense. Oh, I guess it's different then. I think I could have done this then, maybe. Yeah. I don't know. Yeah. I'm gonna read up on the solution, but the lead code solution for that is what I explained. I think I didn't explain it very well, but basically, just to repeat what's already been repeated so many times, it's the reason why we can change. Let's say we find a number that belongs in the 0 index. The reason why we can change it there is because, firstly, it doesn't change the overall length of the largest subsequence, but like if we did this, if we were like at we just found a 1 and we added the 1 where the 3 was, right? If we find a 9, if we find a 9 next, this is still valid because although like it'll be like 4, 5, 6, 8, 9, 1, 9, right? The 3 here. This 1 is just like a placeholder there. This 3 is there, but you can't see it, I guess, because like we just put the 1 there because in the future it'll give us a chance to find a better subsequence starting where 1 is the very first index or very first like number in that subsequence. So I guess that's the lead code one. That's what I read on the solution, but I really want to see if I still remember this in 2 weeks. So the plan is I'm going to just do this these problems hopefully for a day, but I wonder if how well that's gonna go. because yeah, because I honestly had nothing to do today, and it it still took me a good bit. So we shall see. We shall see. Yeah, I mean that's it for the video. But yeah, I'll try to do some more tomorrow, and I'll keep working at this, and you know, uh, yeah, so, yeah, yeah, and we'll see how this goes, and yeah, okay, see ya. It's raining really hard right now.